Who?
No.
Daniil. Sorry, I was just Daniil. And the title is Limited Capacity of Non-Stochastic Steganographic Systems and Hausdorff dimension.
Okay, thanks. Actually, indeed, it's joint work with Boris Ryabko, and the part about Hausdorff dimension is actually more his, but I am going to present it anyway because he didn't come. At first I want to introduce briefly what is steganography, because probably most of you don't know about it, except maybe those who were at the same conference last year. And to those I have to apologize because I used the same colorful example to introduce steganography this time as the last time. So we have two communicating parties, Alice and Bob, which are communicating over a public channel. So public means that there is some observer, Eve, who is observing everything. And so they can exchange messages like this. So Alice can send to Bob something like this. So she's sending this to Bob. And okay, but so this is a very innocent looking message. But now this is not really what Alice wants to do. What Alice really wants to do is to send some secret. And this secret is very disturbing. So she doesn't want anyone to know that she is sending a secret. Not just that she doesn't want anyone to know what she is sending, but the very fact that she is sending a secret, she wants to hide this fact. So practically what people do, they try to hide some secret message into an innocent looking message like this. And so in the beginning of steganography, people were just trying to do it in such a way that you cannot visually distinguish a message with a secret from a message with secret. But it's actually not the goal. The goal is to have a message that cannot be distinguished by any method at all from an innocent looking message, not from the original. So somehow Alice wants to hide this into a message like this, and she can get something like, for example, assume that she is using some steganographic system and she gets something like this. And then she passes this message to Bob. Again, this message is maybe quite innocent. And now Bob discards that and he gets a secret. So he needs some method to decode the secret from that message. And so Eve is faced with the question. So she was observing maybe this or maybe this, one of these two situations, and she has to decide whether there was some secret hidden in this message or not. And so there are different ways to formalize this problem, and also lots of people don't formalize it at all. They just write some software and use some methods. But I will consider several possible formalizations. One of them is stochastic model and a known model case, so where we will assume that this images or cover text distribution is known. The other one is a little bit more realistic, it's still stochastic model, but a universal case where we do not know the distribution of the messages. And then I would like to present some non-stochastic model and link it to Hausdorff dimension of the set a little bit, and some more discussion on some more results, if I have time. So the stochastic model is like this. So we have a secret text X, which is a sequence generated by a source of independent, identically distributed Bernoulli unbiased coin toss. So it's just 0, 1 with probability 1/2. So this is the secret message, that little bomb that she wants to hide. And so this is actually a realistic model for a secret, because normally you assume that if you have a secret, you encrypt it very well, so that it's indistinguishable from random noise. And it can be actually random noise if you use perfect ciphers. Now also Alice has a source mu of cover text. Cover text are those pictures that we had, those innocent looking pictures. And we assume that the probability distribution is completely known. The probability distribution of the source is completely known for now, which is not a very realistic assumption, but just assume that. And we have to encode X in such a way that the output distribution is mu, is this. So what Alice outputs onto the the public channel should have this distribution mu. Okay, and actually the solution is quite simple if you filter out different technical problems with block sizes and stuff like that. The basic idea for solving this problem is like this. Suppose that Alice has an optimal code phi for the source mu, and then she just takes your secret message and she decodes this message. So she applies the decoder to this message. And so if the secret was this, indeed this, fair coin toss, then the output will have the distribution mu. If it was a perfect optimal code for mu. And the number of secret bits per cover text will be h of mu, the entropy of mu. Okay, so now this is a little bit unrealistic maybe in the sense that for this we really need a perfect knowledge of the distribution mu. But now what if we don't know the distribution mu? So we can still solve the problem, but we need to make the assumption that the distribution mu has finite memory. And how the problem is solved, I will explain on a very simple example, which is not really perfect, but is simple. So assume that instead of having images, those photographs, we just have a binary alphabet A, B, of the cover text. And it has some distribution, it has some IID distribution which is unknown. So it means that just the probability of A is not known. And suppose that Alice wants to pass X. This is a secret, so suppose that this is your secret message. Now, what does it mean that she can use mu, but she doesn't know the distribution? It means that she can use, she has an oracle access to mu. So she can use mu to generate some sequence. So she's generating this sequence, whose distribution, again, she doesn't know. But she has this sequence. And so the steganographic method is like this. So if she breaks this into pairs, and if a pair is AA or BB, then she just sends it over the public channel. And it doesn't code any information, she just sends it. But if the pair is BA or AB, then she can pass some secret information. And she does it as follows. So if your secret bit to pass is 0, then she is passing AB. And otherwise, if the secret bit is 1, then she is passing BA. So in the example, she would transmit this. So if there was an AA, she just transmit it as it is. But if these are different, BA or AB, then it depends on this thing what she passes, on the secret. So she passes AB if she wanted to send 0, and BA if she wanted to send 1. And decoding is, of course, very simple. So Bob discards AA and BB and decodes AB as 0 and BA as 1. So we have an oracle access to a distribution which we don't know. We don't know the probabilities, but we know that it's IID. So it's independent, identically distributed. And so using the simple fact that for IID distribution, the probability of VA is the same as probability of AB, we can ensure that the distribution of this sequence, the output one, is exactly the same as the distribution of the input sequence. So that is an easily verifiable result. That it is easy to see that the output of the steganographic system has exactly the same distribution as the input, as the oracle input. And the speed of transmission of secret text is p times 1 minus p, so that's secret bits per cover text, which is much less than entropy. But for this Stiga system, we can extend it to any sources of any IID or finite memory sources of cover text, not just binary and IID, but also finite memory. And we can have the speed of transmission of secret text exactly the entropy, well, in the limit. At the limit of the block size, we can have the entropy of the source as the speed of transmission of secret text without knowing the distribution. But unfortunately, the problem is that these photographic images or human written text and stuff like that that we want to hide information in is not IAD, and it's not even Markov. And so the problem is that the distributions are actually so complex that we probably cannot characterize them in some meaningful manner with our standard probabilistic model. So this means that we would like to have some maybe non-stochastic approach to this problem. Then maybe something else will come out of it. Maybe we will have something new. So in the very early works on steganography, well, very early, something like 98, the following so-called hash steganographic method was proposed. Suppose that Alice has a large collection of text. So maybe this is a large collection of photographs of text that she has already generated. And now she wants to pass a very short secret message. And she also has some hash function. So then what she can try to do is she can take one by one the pictures that she has, this cover text that she has, and apply the hash function to them. And if the output coincides exactly with your secret message, then she just transmits that image. Well, otherwise she just tries another one. And so you can see that this is not very practical because obviously the time this would take and the number of messages she would have to consider is exponential in the size of the secret message. But still, maybe for very short messages like 1 or 2 bits, it could kind of work.
But if no hash function.
If can know hash function, yes. In all these examples, if gets exactly the message, it's not a problem. The problem is
the message, yeah, but hash function is known
yes,
to if.
yes. So she gets the message that is passed. She can apply the same hash function to this
Sasha,
message.
it's MD5.
She can, well, yes, MD5 is not very good hash function, but yes. She can get exactly the secret message, not just the cover text. She can get the secret message as well.
Formal definition.
Okay. Okay, but I'm not yet. So that was just an informal stego system that was considered in many early works on steganography. But there are no theorems about it. I mean, if you actually try to prove theorems, you see that there are some little troubles. But the troubles are not knowing the hash function. So now consider a little bit different model. So in here we also assume that we know the source of cover text very well, but it doesn't have any distribution. Now the source of cover text is actually just a set of infinite sequences. And we want to know how much information in principle for any stego system we can pass using this source, using this set of infinite sequences. And so the theorem is that there actually exists a stego system phi whose speed of transmission of hidden information for such a source is the Hausdorff dimension. And that this is optimal. But for this, we again need to know exactly the set. And well, the idea of the proof is actually very simple, and it's based also on the first decompression idea, is that if you have a perfect code for encoding for this set of infinite messages, of infinite strings, then we can take a string and decompress it, so decode it, and the output will belong to the set, of course. So we take a secret message, we decode it, and since this code was actually a code for that set, so we will get an element of that set. And since the code was optimal, the speed of transmission will be the Hausdorff dimension. So as with the stochastic case of the known source, the idea is very simple. You just have a very good code already, and you sort of solve the inverse problem, because in order to pass a message, you use a decoder instead of encoder. and the speed of transmission is going to be optimal if you use an optimal code. Okay, and so this is basically based on the result on universal codes by Boris Ryabko, which is a pretty old result. Now, what can we pass to yet another setting? So what can we say about computable methods for sources of hidden of cover text that are not IID or Markov? And so far here we only have a negative result that basically says that, well, we have an impossibility result that basically says that it's very difficult. So if you have a source of cover text which is not IID and not Markov like we had in our example, but which is still some stochastic source, then it is very difficult, it can be very difficult to encode secret information into this source, despite the fact that actually we just presented some simple steganographic methods. And so for this we will consider the following model. So now our cover text are strings of finite length n, and we have some distribution on these strings, which is an oracle distribution. And so Alice can generate using this oracle a message and a cover text, and then she wants somehow to encode your secret text into this message. So either she discards this and writes something else, or she uses the message that she generated from the oracle to somehow construct a message that codes your secret text, but in such a way that the output distribution should be the same as the input distribution.
But oracle is sampling oracle, or
yes,
it gives the probability.
No, it just gives strings. So you only
generate strings.
Yes,
doesn't say the probability of any string.
She doesn't get any probability. She just gets one string. Like with a photo camera. She takes picture, gets one message, one string. And now she has somehow to put her secret into that. Or she can also completely discard the message and what she got from the camera and pass something different. But what she wants to have is the same distribution on that. Okay, and so a theorem is that if you want to have a linear speed of transmission in this n, which is the length of the string, not just optimal, but at least linear, then it is very difficult with computable methods in the sense that there exists a family of distributions on these strings whose entropy is pretty high, and any stego system whose complexity is sub-exponential and whose speed of transmission is linear in n is not secure. Is not perfectly secure, which means that the distribution on the output will be different than the distribution on the input. Well, I just give a very small proof idea, which basically says that we can show that in order to save the distribution, to have the same distribution on the output as on the input, you need to know the distribution on the input. And if you need to know, and the distribution on the input can be very complex. So if you just take a random subset of the set of size, whose size is 1/2, then its Kolmogorov complexity is maximal, and effectively we can show that Alice needs to know a large portion of this set to have the same distribution on the output. Well, so I'm already at the conclusion. So I had quite a few settings in a pretty short talk. So the main message I wanted to pass is that entropy, Hausdorff dimension, and Kolmogorov complexity appear as fundamental characteristics in many problems that you know and love, I hope, such as data compression, prediction, randomness extraction. And so now we're adding one more to the list, and this one more is steganography. And so in a way, steganography can be seen sometimes as the inverse to data compression, as I have shown, I hope. But it is also related to randomness extraction, because the methods with pairs I was showing you is based on von Neumann method for randomness extraction. And we get entropy, Hausdorff dimension. We don't really get Kolmogorov complexity so far. as a speed or as a limiting speed of transmission of secret text, but we already used it a little bit. But also an important message is that there are lots of open problems in steganography, and the main open problem is, of course, to construct an efficient non-stochastic stega system, which doesn't mean that you actually have to write a software. Maybe you can just prove some theorems in which you don't need to know precisely the source of the cover text as we did here in our example. So this is it.
Are there any questions or remarks?
I have a question about the challenge.
Yes.
So can you specify, say it more specifically, what kind of mathematical object you would consider an efficient non-stochastic stega system, which will be somehow a solution of this challenge, and preferably it should be the non-existence of such object shouldn't be obvious. So just what thing you will be satisfied with.
Well,
so I believe it can happen.
So unfortunately, the main problem is here also to find a good formalization. So I cannot give you a precise open symmetrical problem for this. Probably if I had one, I would have solved it already. But so what I would be satisfied with is some maybe natural description of the quite complicated situations where your stega system gets as an input a long string, which is a cover text, and she inputs, and you input some secret text there, such that the output still belongs to the set of feasible or good enough cover texts. So there is some unknown set of cover text. You get one as an input. You have to output one as well. So this second one that the output should belong to the set.
But first, in this setting, it's obvious that you cannot send something which you haven't seen.
Well, sure, you can. I mean, for example, in the IID example, we are sending something that you haven't seen.
No, so, and you know the distribution, but you say
no, we don't know the distribution.
You know some properties of the distribution.
Yes.
Something have the same probability.
Yes.
But probably in your setting, when that's not just you get the text, not the distribution, you never can know this.
Never can know.
So there is no chance no possibility of sending something which was not seen, because
well, so the meaningful formulation will of course include this. Will of course include the possibility of sending something that you haven't seen. Otherwise, it's not really interesting.
But then you need to specify the model.
Well, that's a problem. I mean,
it's a practical problem or theoretical problem. Let's be serious.
Well, so okay, if you want a theoretical problem, that is.
Yeah, I want either, but I want to be either clearly theoretical or clearly practical.
Well, so to me there is a clear problem in between to define a good problem that would at the same time describe your correspond well to your practical problem and would have a meaningful mathematical solution.
Okay,
and probably lead to
some non-practical problem.
The non-practical problem, yes, steganography. It's on my first.
Can you just give some specific example of what people were doing, or what was the achievement, or just some more specific?
So at first people were doing things like this. So you have a text, you have an image, and you want to embed a secret text. So they were saying that, I think that the last bit of each pixel is uniformly IID 1/2, which is not true. And so we just write the secret there. And so it means that you get an image, you pass an image, and actually what you pass looks exactly the same, but it's very easy to distinguish it with statistical methods, with practical software from image that was not tampered. So in a way you got something and you're sending something different, but something different looks very similar.
Yeah, so you just want some software which transforms picture and a message and get a picture so it cannot be distinguished from actual thing, yeah?
Well, cannot be distinguished by statistical methods, yes. Well, if I give you this and you as a result of your steganographic method, you gave me something completely different, it would also be fine as long as it's also a picture that looks normal.
Okay, but you know that for example, standard pictures have some noise.
True.
So,
And that's what people are trying to do. They try to somehow use this noise to pass secret information. But the problem is not solved because people were, for example, embedding, like I said, in the last bit, and they were thinking that it's perfect, but it's actually very easy to distinguish with statistical methods, just looking at the distribution of this last bit and it's different. Then people try to estimate the distribution and imitate the distribution and so on, but so far there is no steganographic method that is
but you can only
probably
send
secure
pictures
this.
with this noise. But it could be a message or random noise, then it will be distinguished.
What do you mean? If there is some noise that is perfectly random, then yes, but it's not practically.
No, but you can each time add a noise to the protocol with the same algorithm.
Add noise where?
No, you just in your photo before sending anything, you always add the noise.
Okay, so you show a picture with the noise and then you take a picture.
Always your photo camera makes pictures with noise.
Right.
Sometimes this noise is replaced by the why is not a solution.
So far the practical solutions have practical attacks on them, and attacks are good. So people just estimate the distribution of the noise in normal messages, innocent ones, then they estimate they look at the noise in the message that you're tampered with, and they distinguish quite well these two cases. But, okay, if you want something positive, if you have two pictures, then with our method here, you can pass one secret bit by just the order of the message. And if you have n messages, then you can pass log n factorial bit in the order, like in here. So there are some situations in which you can pass secret bits. For most practically interesting situations, there is no method so far. So there is a place for both theory and practice.
So couldn't you actually use this just with the noise which is already in the picture and just like flip the bit, the last bit according to this?
Yes, so you can use this. It would be probably secure if the noise were IID or Markov. But we don't know if it's IID or Markov, and apparently it's not. So.
Any other questions? Or no? Well, then I'd like to thank the speaker once again.